Hello everyone, it's a proof essayist here, here with another coordinate geometry proof, which in my opinion is a war of attrition, because I made so many mistakes making this video through the thing. It's a pretty hard problem in my opinion, because depending on how you define your coordinate system, your method in showing this theorem is true could be vastly different from mine, but that's just how it goes. So let's define what a median is. I think it works for a polygon, but for a triangle at least, it's a line segment that joins a polygon's vertex with its opposite side's midpoint. So for this triangle here, corresponds to this line segment here from the origin up to here. That's just one example. And we want to prove that in a triangle, if two medians are congruent, then the triangle is isosceles. Two congruent sides and two congruent angles. But all that's sufficient is to prove that the two sides are congruent. If you do it with angles in coordinate geometry, you're going to have to apply that very nasty formula that involves tangent of theta and the slopes. And there's two versions, and that's really nasty. You can't even set them equal to each other because tangent of theta is not bijective. Those who know their discrete math and stuff can go and see why it's not. But it's just nice. It's nasty. So I think it's good enough just to show that given two medians are the same, that two sides of the triangle are the same. That's sufficient enough. And as usual, we're going to start showing that the squares of the distances are the same to make our lives easier, because that way we can avoid dealing with the square roots. But yeah, I call this line segment here median 3, this line segment here median 2. We're going to take their squares and set them equal to each other and find out what they can give us now. So median 3, a over 2 minus b squared plus c minus 0 squared. And now for median 2, that's going to be b over 2 minus a quantity squared plus c over 2 minus 0 squared. We don't have to be very careful about the order that we put them inside the squares, because the square of a negative is going to be a positive. What I'm going to do now is move the terms with a and b's and c's all together, and you're going to see what I do next, which I think is cool. Squared minus b over 2 minus a squared equals c over 2 squared minus c squared. Well, now basically I have the difference of two squares here on this side and this side with kind of similar terms. So now, oh yeah, first let me write what difference of two squares is. If I'm given that x squared minus y squared gives something of this form, then I can rewrite that out as x minus y times x plus y. Okay, now I'm going to have to erase that, unfortunately, to make room right over here. But yeah, I can re-express this out as a over 2 minus b. I'm going to do the positive side first, so I'm going to add plus b over 2 and then add minus a, so that's just minus a. And now I'm going to do a over 2 minus b. I just copy that here, but now subtracts everything else. So that's minus b over 2 minus minus a, double negative becomes positive, that's plus a. And then c half minus c half squared minus c squared. That's good. That's c half minus c half plus c. And now we go and simplify everything out right now. This is going to be 1/2 a. Actually, I believe is a minus half a. And if I do minus b plus b half, that's going to be minus half b. Now if I do it on this side, a over 2 plus a, that's going to be 3/2 a. Here it's going to be minus 3/2 b. And now that's going to be minus 1/2 half C times free half C. And that was very nice because we both get a minus a half and a free half on both sides of the equation that we can factor out. And this free half or 2/3, that's a very typical thing I think I remember seeing in like proofs involving medians. So you should be happy to see that number pop out, though it's kind of inconvenient that you have to cancel it out in the end. So anyhow, we can get minus 1/2. We can get a free half here. That just leaves us with a minus b times a plus b equals minus a half times free halves c squared. All of this disappears. And we can re-expand this out as a squared minus b squared. That equals c squared. Now, how is that useful for us? Let's take a look at the sides of the triangle now. A squared minus b squared. Actually, let's do c squared first. Where do we see c squared here? If we take a look at s2 squared, as the value of s2 squared, that's basically c minus 0 plus b minus 0 squared. And we take a look at s free squared. That's simply a minus 0 squared plus 0 squared, so just 0 squared, period. And then that just becomes s2 squared simply equals, oops, I forgot to put a square here, c squared plus b squared s free squared equals a squared. And given this relationship, I can put in the plus b squared on both sides. So I get a squared equals c squared plus b squared. But we've just shown over here that s2 absolute value squared and s3 absolute value squared are two things we can, that c squared plus b squared, sorry, I'll repeat that again. We've just shown that c squared plus b squared and a squared are values that corresponds to the side lengths that are opposite the medians, or that the medians bisect. So we can say from this that absolute value of s3 squared equals absolute value of s2 squared. So thankfully, this side and this side are congruent to each other, and we are done.